Hit record. All right. Well, I will begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for this class. Just ask you to bless our work today. Help us to glorify what we do, and just to understand a little bit more about multilinear algebra and tensors today, Lord. In your name, pray, Lord Jesus. Amen. All right. So I'm going to follow my notes because, but just so you know, let me just get the definition out here. I guess I should wait because this definition presupposes something that some of you guys probably don't know yet. And so before we can talk about multilinear algebra, we need to just talk a little bit about the dual space. So here's a definition. If V is vector space over R, then V dual, which is denoted like this, is equal to the linear maps from V to R. All right, so what we're talking about is alpha, a mapping from V to R such that alpha is linear. All right. Now, if V is finite dimensional, if V is a finite dimensional vector space, then the dual space is also a finite dimensional vector space, and in fact, it's isomorphic to V. I won't belabor this much, but just say that this is something we can construct the dual space to a vector space. Now, here's the main construction we need to know about. Definition. If V is the span of E sub I. By the way, in this lecture, I am not going to be assuming that E sub I is necessarily the standard basis. I'm using E as an abstract basis here. All right. Oftentimes it might be the standard basis, but it doesn't have to be. Okay. So if V is the span of EI, then E upper I is a mapping from V to R defined by E upper I of E lower j is equal to Kronecker delta ij extended linearly. So here, if beta is E1, the ordered basis E1 through En, then beta dual is the dual basis, E upper 1, E upper 2, E upper N. All right? So here we go. Basis for V, over here, dual basis. For V dual. All right. The dual basis really are just component functions for the coordinate maps of the beta basis. If you study it, let me see here. What should I prove? Let's look at how the formula works out for this notation. I should mention in Paul Rentelen's book, he uses theta, like theta upper I, for I think in Rentelen's book he's got like these ones, he's used like a theta upper I for these. And I think he's used E lower I for those. All right, so that's to translate the notation, yeah. But I know I've used E upper I in much of what I've written, so I should talk to you about that. All right. Okay. So before I get any further, let me just give you a so mostly today I'm going to be talking to you about multilinear algebra. But eventually we want to apply these things to study what are called tensor fields. All right? So a tensor field is like attaching a tensor at each point along some space. All right? So eventually, instead of just looking at a vector space, this vector space is going to eventually, in our application, the vector space is going to become the tangent space. It's going to become the tangent space. What'd I do?
I was biting this kiwi with the skin on it.
Oh,
This
that
is
is,
edible. It's hairy.
that is,
That's why you rub it.
that is true.
It is good for you.
That is true.
That is, wow. What are the odds? Okay, anyway.
The kiwi skin relates more to this topic.
Man, goodness gracious. So the tangent space, we will think of the tangent space as being the vector space when we apply this algebra in future lectures, all right? So the tangent space is going to be what plays the role of the vector space. And the dual space is what's called, corresponding to the tangent space, there's something called cotangent space. Cotangent space will be the dual space. I think it's worth saying just a word or two here so you aren't surprised when we make this transition, like next lecture, or not next lecture, it's going to be a bit, I think, till we get back to this. Maybe after spring break, actually. I forget my plan. But for the tangent space, it turns out that the tangent space to P at M is the span of the coordinate derivations, partial, x upper I at P. And the cotangent space, it turns out, is the span of the differentials, dx upper I at P. And in fact, the coordinate derivations, the differentials are dual to those, in the sense they're the dual basis. And this all works together when you combine it with what we call the exterior calculus. So some of the things I'm doing at an algebraic level later get wrapped together with calculus identities. But for now, I don't want to be writing partial xi everywhere. I'm just going to write E. But we're going to think of this eventually being tangent vectors attached to a point. And these are going to be cotangent vectors attached to a point. All right? So let me actually prove something. Let's look at a calculation. Let alpha be a dual vector. All right? Then let's let x be a vector. Alpha of x is equal to what? We have alpha of the sum I equals 1 to n of x upper I, e lower I. So I think I use I do use up-down notation here, so I'm going to have to do this. So we're going to put the index up because it's a vector, all right? It's got this is a convention we're going to start using. The components of vectors, the index is up, okay? Now, alpha is assumed to be a dual vector, which means it's a linear map, right? So I can pull the summation out, and I can pull the constants out. X of I is just a constant, right? So this is the sum, I equals 1 to n, of x upper I, alpha of EI. All right? Excuse me. Now, this can be written actually as the sum I equals 1 to n. I should have done a lemma before I did this. My bad, guys. Alpha of EI, E upper I acting on x. I'm going to explain this step further in the lemma soon to be announced, okay? So allow me a bit of time travel here by lemma. So what is that? What I put in the blue parentheses just now has to be alpha. See? So this is apparently alpha, because this holds not for one x, but for all x. So if we set alpha sub I equal to alpha of ei, then we find that alpha is equal to the sum I equals 1 to n of alpha I, e upper I. So this goes to, I claimed that this is a dual basis, which means it's a spanning set, right? And it's also linearly independent. This shows that, in fact, it is a spanning set, right? Because we can build any covector as a linear combination of the dual basis. All right? Linear independence is pretty easy to prove. We could prove that next if you want. I should do the lemma first, though. Lemma is important. All right, here's the lemma. If beta equals to E1, En is basis for V with dual basis, beta dual equal to E upper 1, E upper n defined by E upper I acting on E lower j equals to Kronecker delta ij. Then, if x is equal to the sum I equals 1 to n of x upper I, E lower I, then x upper I is in fact equal to E upper I acting on x. In other words, the dual basis is the component function of the coordinate map. Right? Remember the coordinate map? So, side comment here. We had this notation before, like phi beta of x was equal to x1, x2, xn. That's the coordinate vector of x with respect to the beta basis. What?
It just is in linear.
Oh, good. Hooray. So, this tells you that if we look at the ith component function of this, it's equal to, x upper I. My claim is that that's equal to ei of x, right? Claim. I haven't shown it yet. Let's prove that claim, okay? How should we prove it? Linearity, yeah. Okay, so let's look at it. E upper I acting on x is equal to E upper I acting on the sum. I better use j here because I already used up the I, right? Sum j equals 1 to n of x upper j, E lower j. My notation isn't entirely in concert with your linear book either. I just can't bear the up-down basis notation for the matrix. Like, I want to do it, I just haven't implemented it yet. But anyway, there's not really much multilinear algebra in your linear algebra book anyway, so it's kind of irrelevant. But okay, so this is assumed to be linear. See, my definition says extend linearly. This is a theorem of linear algebra. If you have a function which is defined on a basis, there is a unique linear extension off the basis, right? Defining what happens on the basis defines what happens everywhere if we assume linearity. So I'm assuming linearity, part of the definition of the dual basis is I can pull that sum out. And I can pull the xj out. This is by the linearity that's built in, that's baked into the cake of the dual basis, Like that's by definition of dual basis. Definition of quote unquote extend linearly. all right? But that is the Kronecker delta by construction, right? And the Kronecker delta is the natural enemy of the finite sum. And as such, all you're left with is an x upper I, and we're done. Eh? All right. So this is dual space, and we could blather on about its properties longer, but I think that's enough. All right. I'm going to turn the page here, talk to you guys about what is a multilinear map. All right. What is a multilinear map? So, what? It's a pyramid scheme? An MLM? Oh, multi-level marketing, yeah. Good point. Yeah, I don't want to get associated with that, that's for sure. Let's see here. Suppose, sorry if you, are you guys into the essential oils? Yeah. My mom does the essential oils. Let's see here. She swears by them, though. Okay, anyway, let me not digress. These are vector spaces. So I'm going to give the definition in a little bit more generality than we need, okay? Then T, mapping from the Cartesian product of V1, V2, Vk to R is a K multilinear mapping on V1 cross Vk if for each C in the reals and x1, y1 in v1, comma, dot, dot, dot. Good grief. Let me rewrite this as each xj, yj in vj for j equals to 1, 2. So I'm saying I've got a pair of vectors in each vector space for the sake of discussion. All right. We have T of x1 dot 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 cxj plus yj comma dot 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 comma xk is equal to, sorry about the double equals, that's the kind of thing that bothers you. But I'll be keeping my double equals right there. X sub j, xk, plus, you know who you are, Violet, x1, yj, xk, 2 equals. Actually, you know what? This is a half of an equals here, and this is a half of equals here. Does that make it better? Okay. The top, no, that would be dangerous notation. I think it's minus. Be like plus, yeah. For j equals to 1, 2, da 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 k, this identity, right? Let me put this into words. I'm assuming K multilinear mapping is a mapping that is linear in each entry. It's linear in each slot. All right. So if, here's the furthermore, if T is multilinear on V cross V cross dot dot cross V. I don't need 2 V's. Let me just do V cross dot dot cross V cross V dual cross da 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 cross V dual, and suppose that there are R fold of these and S fold of those, then T is an element of T upper R lower S V, and we say T is a type RS tensor on V. Now, this is exactly the point I was bemoaning before class, because sadly, it would seem Rentlen has the opposite meaning of R and S. And I'd love to say Rentlen is the industry standard. It may well be, but I have seen it different in different books. So this is the choice I made in my notes, and if it's not the right choice, I'm sorry. Right? It's a choice I made. So okay. So with this language, what's alpha an element of V dual, right? Is a what? What kind of tensor would it be?
0.
So it's a linear map, right? From where? From V to R, right? So we have R equals to 1, S equals to 0. It's a type 1, 0 tensor. Is this opposite anything you're reading? You don't know? You're not sure? All right.
I think
Did I just mess it up?
Rental, what Harry said is correct here.
Really? You think I should? So you're saying?
I think you should rewrite all of your notes.
All right, I'm open to it. Like we can.
Well, I was joking.
Oh.
But I'm not joking. I mean, it makes more sense to have like the R, like be with the not code thing, like you're talking over there. Like how we
Yeah.
Like the S to be with the O.
All right. All right.
See,
Let's do it. Let's do it. Oh my goodness. Oh. All right. Let's fix it now. Oh man. I knew this was going to happen. All right, just a second. I got to look at page 33 in Rentlen. I really have to look at his equation 2.10. So I'm going to write down equation 2.10 and explain to you my logic, all right? And then we can decide together whether or not we need to do this horrible thing you're saying. All right, so equation 210, and this is getting the cart before the horse a bit, but we have a tensor T, which is equal to a sum over I1 through IR and J1 through JS of T upper I1, I2, IR, lower J1, J2, JS. And then we have bases E lower I1 tensor, E lower I2 tensor, E lower IR tensor, for him theta, but I'm going to write it as I would write it, which is E upper J1 tensor, E upper J S. All right?
I like your logic.
So the thing is, if we look at this, this is a mapping actually. So there's an idea called the double dual we need to introduce here to make complete sense of this, which is we're actually going to think of vectors also as active objects. Like dual vectors are naturally linear maps, but we're going to identify a vector as actually a mapping on the dual vectors as well. In the interest of making some heads in here explode, mission accomplished. Ha 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 ha. Let's see here. So where was I? So this actually, this if as a mapping, this would take in these guys, all right, and these would take inputs from V, all right, and so I would need in this lingo R fold of these and S fold of these, all right. So if we're gonna match up with Rentelin's notation, this is the system of notation I have to use. See, so I need there's some somewhat sizable adjustments I have to make in my definition, you see, because I have to reverse, see, it's not, I can't just erase the R and the S. I have to also put the stars over here and, all right, let's do it. I think should I do it? Is it worth it? I don't know.
I mean,
I did assign you guys homework problems from Rentelin, but I've also assigned you homework problems from my notes. So that's where the fun is. Yeah.
You could just write Rentelin's homework problems in your format.
I
That might be easier to do.
yeah, rewriting your whole notes sounds kind of like.
hear follow the book. All right. So let us adjust my definition so it's in tune with Rentelin, and we should just keep this in mind as I talk about a type RS tensor. We need to like flip it, all right? It's not, I don't think it's a big addition. So here we go. We just put stars here. Erase the stars here. And there we go.
So then you would also flip them over there?
No, that's from that's from Rentelin.
So I guess the upper and lower indices on the T thing is talking about what it maps where.
That's the thing is, okay, so there are two different things to think about. So here's the two different things to think about. The one thing to think about is the components of the tensor, right? These are the components of the tensor. And then, of course, this is the basis. Like, I don't know, what's the word for it? The basis element for the tensors. Let's see here, my notation. Well, he calls it TRS, which I guess I have as well, right? So the Rentelin doesn't have the V there. I put a V because, yeah. So yeah, we can do this. So that makes the dual vector not a 1, 0 tensor, but a what? Yeah. So we have 0, 1 vector and 0, 1 tensor. And conversely, if we had X an element of V, is, check this out, a linear map. This is the weird part, guys. It's a linear map from the dual space to R via the rule X of alpha equals to what? Alpha of X. That's what it has to be. Because alpha eats X, right? I mean, X is a vector, so we know what alpha of X means, and that is in fact how we define the vector X on the form by the form acting on the vector. It's annoying. Now, if you wanted to, I could put a hat on this so I can distinguish between X and X hat, right? But there's obviously a one-to-one correspondence between X and X hat. This being an element technically of V double dual, and X being an element of V. So the double dual is canonically identified with the vector space. I don't really want to make more of this than it is. I just want to show you some formulas, and we'll get used to working with it, and then it won't be too horrible, actually. But with that adjustment, the vector is a what? It's a type what? So like x hat is a type 1, 0 tensor. All right. Yeah.
If you consider that x hat on x, it wouldn't be a type 0 and 1 here because you're using v dual.
Oh, what did you ask me? Would it be a what?
If you're treating x as a double dual, then wouldn't that make it a 0, 1 because v dual is your vector space?
No, because this is all with respect to v. We don't talk about v type and v dual type. It's always with respect to v. So, yes, if I talked about everything with respect to v dual, rs would become sr. There's a natural transference there, but let us not get into that. All right. Well, I feel like this lecture started out well, and then something horrible has happened. Something I will regret with every page I work through. We're gonna try to stick with it. All right, so for the record, I did spend several hundred hours editing these notes before this semester. I really did.
How long would it take you to fix this? Is it going to take you like a long time to go through and this other stuff?
No, I don't know.
What if we just do the trick we did today, where you just go the replace button?
Okay, so let's go on here.
Replace like all the R's and S's.
You can do that.
So I actually don't think it's really much of an issue. It's really just a matter of bookkeeping, to be truthful. So like, let me show you some examples here. Example, what am I on? 2? If we have B is a mapping from V cross V. Oh, rats, I'm sorry. Now you guys got me off. You got me off my storyline. So I needed to introduce, I used this, I threw a tensor product over here, and I owe you explanations for what on earth these things, how we define these, right? So let's define what that means. So let's talk about building multilinear maps via the tensor product. So, all right, I'm just going to illustrate by cases. I think that's probably the best. If we have alpha and beta are in V dual, then alpha tensor beta acts on a pair of vectors x, y as follows. Alpha of x, beta of y. Simply like that. So alpha tensor beta, we can prove, is actually a mapping from V cross V to the reals. And in fact, this will be a bilinear map. In other words, a 2-linear map. Can you see why alpha tensor beta is linear in both slots? It's kind of silly. We are assuming alpha is linear. We're assuming beta is linear. So if I put in a linear combination into the x slot, we can break that up. If I put a linear combination into the y spot, we can break that up. And let me do it. Alpha tensor beta of x comma like c1 y1 plus y2, right? Is by definition alpha of x times beta of cy1 plus y2. I mean, I can say these things, but I should write them out so you guys make sure I'm not losing you. C beta of y1 plus beta of y2, right? And then these are just numbers at this point. So I've got C alpha of x, beta of y1, plus alpha of x, beta of y2. Joking aside, there's probably a pretty good chance that whatever convention Rentelin has picked in his book is the dominant one, and the one I should probably try to center this course on. So I think it's worth my time. I'm not just joking. Like, I really do think it's probably worth it. So we'll do that. Just my apologies in advance if I miss it somewhere or something, right? So we'll have to double check on that.
That's what Violet's for.
That's what Violet's for. So we have C times alpha beta of xy, 1, plus alpha tensor beta of x comma y2, right? And that's what we want. That's linearity in the second slot, right? Linearity in the second slot. And similarly, we could prove linearity in the first spot. But I thought the second slot's kind of the more slightly non-trivial one, right? So this gives us a way of taking dual vectors, right? We can take dual vectors and we can build from dual vectors bilinear maps, right? Is every bilinear map simply the tensor product of two dual vectors? What do you think? I saw immediate head shaking. No, it can't be. Why do you think not? The structure of my question, just a good guess, or you have some kind of feeling?
Yeah.
Just feels too easy? Yeah.
Well, you did say multilinear maps.
Mm-hmm.
So there must be something for 3 or 4.
Oh, well, this is true. We could take the tensor product of 3 dual vectors. What would that be? If I had, say, alpha, beta, gamma in V dual, right? Then alpha tensor beta tensor gamma would act on, say, x, y, z vectors, according to what you guys tell me the rule. I got an alpha of x, I got a beta of y, I get a gamma of z. Correct. This defines alpha tensor, beta tensor, gamma as a trilinear map on V. You can easily check that it's linear in the x, the y, and the z. All right? So this brings me to my next question, which is every trilinear map simply the tensor product of 3 dual vectors? What do you think? Yeah.
It's a linear combination of them.
A linear combination of them, Sam says. I think I want to believe that. Let's prove it. So here's a calculation that we can do. Let's start with a bilinear map, an arbitrary bilinear map. So consider, I'll use a big B, a bilinear map from V cross V to the reals, all right? Bilinear. Which in our current language is a what? A type what tensor? Type 0, 2 tensor, I believe. Right. If 0, 1 is a dual vector, this is kind of like a double, like it's kind of like putting 2 dual vectors together in the tensor sense. Okay, so, right? 0, 2. No input is a dual vector. Both inputs are vectors. All right, great. So check it out, yo. If we have b of x comma y is b of, how about this, sum of x upper I, e lower I, sum of x upper j, e lower j, like so. By bilinearity, I can pull out the sums, and I can pull out the constants. And I can use my handy-dandy lemma a second time and a third time. Let's write that b lower ij of e upper I acting on x times e upper j acting on y by my lemma. Lemma says x upper I is ei acting on x, y upper j is ej acting on y. Yeah? Oh, yes. Thank you, thank you, thank you, thank you. Yeah, if you see something, say something. Let's see here. What? Did something happen today I don't know about? I mean, I know Gene Hackman died, but... Oh, yeah. They found him dead in his house with his wife and his dog, apparently.
His dog killed him?
Well, his dog. His dog killed him. I like the way you think, Preston. What's that?
He was in cahoots with his wife.
Well, he was 95. His wife was 64, and I was reading reading his comments, and the comments were like, so this is obviously like carbon monoxide poisoning, and that made a lot of sense to me because it's like they live out west, it's cold, probably just put a heater on, and I mean, if you're gonna kill each other, you don't usually kill the dog, you know? I mean, and he's a 95-year-old actor. He's lived a good life. It's like the likelihood of suicide pact is pretty low, you know? Anyway. Do you guys even know who Gene Hackman is? No. See, I didn't think so.
I've heard the name, but I'm not matching the face right now.
He was the villain in the Superman franchise that you guys haven't watched.
Which franchise? You're right.
The one you haven't watched.
The one with the curls.
The one that's like the 1980s really like the 1980s one, you know, with Christopher Reeve and all that junk. I have not seen those movies. I think I saw the movies when I was like 10 on TBS. I think it was like the last time I seen it. I don't know. It's been a while.
That's like negative 30.
Yeah. 35-ish. Okay, so. Oh, man. So this is an identity that holds for all x and y, right? So therefore, B is equal to the sum over I and j of Bij, E upper I, tensor E upper j. Where Bij is equal to B of Ei, comma Ej. Those are the components of the tensor, B lower Ij. The question? No? Okay. So yeah, it looks like you're both right. We can't use a single, probably we can't use a single pair of dual vectors, right? Like we need to add together a bunch of tensor products of dual vectors in order to get a bilinear map, right? Yeah. I believe the minimal number of, I think I'm trying to think, there's like you can define rank for a tensor in terms of how many dual vectors you need to tensor product and add together in order to get it. And that probably has something to do with like the rank of Bij as a matrix as well, but maybe not. I don't know. Like that stuff I don't know very well, so I'm not going to say more about it. Unfortunately, people used to say that if you read some of the older things, like they'll call this a rank 02 tensor. That's not good language. We shouldn't use that language. We should say like type 02 because rank has more the idea of like dimension of the column space, that sort of thing, and we don't want to confuse those issues. Anyway, so there's that. What would it mean for this bilinear map to be symmetric? I hear to Bij equals to Bji, but can we define it? Like what's the, whoa, oh man. I almost got it. Alpha equals to beta. No. So definition, if Bxy is equal to Byx for all x and y in V, then B is symmetric bilinear mapping on V, right? And likewise, if B of x comma y is equal to minus B of y comma x for all x and y in V, then it's what? Yeah, B is an antisymmetric. Antisymmetric bilinear map. All right. Yep.
Does this hold for the trilinear?
Yes. The definition of symmetry and antisymmetry for trilinear is more complicated, though, because to say it's completely symmetric means that any exchange gives you the same result. But to define completely antisymmetric, I really should talk about permutations. So like, but yeah, we could define this more generally. If you have T is a tensor, you know, and V1, V2, Vk are inputs to the tensor, and that's equal to T of Vi1, Vi2, Vik, right? Where I1 through Ik is just a reindexing, right? A permutation, like I1 through I1 through Ik is a permutation of 1 through k. If this is true for all possible permutations, this is said to be a symmetric tensor, symmetric k-tensor. On the other hand, if you have to put the sign of, let's say, I here, then that makes it a completely antisymmetric tensor, where the sign is defined to be plus or minus 1, depending on whether or not the permutation can be written as an even or an odd product of transpositions, which we define in Math 421. My apologies. But the antisymmetric, if you read my notes, I have more, like for 2 things, it's just a minus. For 3 things, anyway, I don't want to talk about that issue today, so let me just leave it at that. There's a page in my notes where I describe that in more detail, but another way to say completely antisymmetric is that any interchange of the inputs gives you a minus. That's also a sufficient definition. It's completely antisymmetric if any swap of inputs gives you a minus in the outcome.
So it'd be like antisymmetric if any 2 were swapped, and then like fully antisymmetric if they're all swapped.
So if it's fully, excuse me, if T is antisymmetric and it's got 3 things, right? Then this is like minus that, which is minus also, which is also, which is also, if I just, because I just swapped these 2, so that gets me minus is plus. Sam's like, can't you just write Vi, Vj, Vk equals to epsilon ijk, T of V1, V2, V3? Won't that suffice to capture the complete antisymmetry of a trilinear map? The answer is yes. This is a way we could formulate complete antisymmetry. We could use the Levi-Civita symbol. The thing that is the glue that holds the determinant together can also define complete antisymmetry. We're getting into a chicken and egg kind of thing, though, because essentially that's what the determinant is the completely antisymmetric n-linear map. And you can prove that there's a unique one of those that sends the identity matrix thought as n inputs to the number 1. That uniquely defines the determinant. But you guys have got me into the future. A future we may not even go to. So let me get back to the main storyline here. So all I was trying to say is we can talk about symmetry or anti-symmetry or symmetry, and it will be reflected in the components. So you guys told me, like, you know the deal. B EI EJ is equal to BIJ, right? So if we have, that's going to be equal to BJI if symmetric, right? And it's going to be equal to minus BJI if it's anti-symmetric, right? For all ij. Yep.
Would it be the case that it doesn't equal either of those?
Yes, you can have mappings which are neither bilinear nor neither symmetric nor anti-symmetric. However, an arbitrary bilinear map can be written as a sum of a symmetric and a symmetric and an anti-symmetric map according to the following rule. You just do 1/2 of bxy plus byx plus 1/2 of bxy minus byx. And you can prove that this is symmetric and this is anti-symmetric. Therefore, any bilinear map can be rewritten as a sum of a symmetric and an anti-symmetric bilinear map. The next question you'd ask me is, what about trilinear maps? Is it possible to write any trilinear map as the sum of a completely symmetric and a completely anti-symmetric trilinear map? There, the answer is no. And to answer exactly what the structure of a trilinear map is in general is the problem of representation theory, which is far past this course. That's hard linear algebra, actually. So I won't say anything more about that except to say that it can't be done. And that I have asked homework questions about this in the past that I have regretted. I will say that as well. Yes, maybe there. All right, so we should talk about coordinate change, all right? Because we have everything we need to talk about coordinate change now, because given a tensor, see, like this over here. I'm sorry, so you guys, I've neglected to take the next step. So I talked about the tensor product of dual vectors, right? What would the tensor product of vectors mean? Like if I have, and I could put hats on these, but we just won't, okay? Because if we start writing hats on everything, you won't like it, If you want to, you can put hats on them to distinguish them from x and y, but I'm not going to, okay?
Or maybe just to distinguish them from commoners.
I don't know what just happened here, but so what if I have two vectors x and y, I take their tensor product, I'm telling you that that defines a mapping on pairs of dual vectors. What's the rule? Yeah.
X alpha y. So x alpha y.
Oh, so you're like x of alpha, y of beta. I see. You're not wrong, but we don't really want to look at it that way because that just begs the question, what do those mean? So instead of writing that, we will simply get to the point, which is to say alpha of x, beta of y. All right. And if you can, and this would make x tensor y a type what? Yeah? What do you got? But 2, 0. Yes, a 2, 0 tensor. I'll get out of the way. You lost your chance. But so type 2, 0 tensor. And we could go through the same calculation I just went through, right? For a what? If we let's say, I used B already. Let's use a different letter. I don't know. What's that? G. Oh, interesting. G, capital G. So say G is a bilinear map on the dual space like this. So suppose it takes in pairs of dual vectors, right? We could write down that as a sum of tensor products of the dual basis. Excuse me, not the dual basis, the tensor product of the basis. So this would mean G is equal to like the sum I comma j of g, I think we want an upper ij this time. And then we're going to have e lower I tensor e lower j. So theorem. And where g upper ij is defined how? It's g of e upper I comma e upper j, where those are the dual bases, yeah? Yep.
So in that definition, you say the left-hand side equals alpha of x, beta of y,
Yep.
and which is the same as over here.
That's right.
So
That's on purpose.
they're equal.
They are equal in terms of their outputs, yeah. But, I mean, however, x tensor y is not equal to alpha tensor beta. I mean, that's not true. These are different objects. This is a type 2, 0 tensor. This is a type 0, 2 tensor. They're different things.
Yeah.
They operate on different pairs, but if we make the pairs match up, it is true that their output is the same, yeah.
On the reals.
No, for the given 4 things, alpha, beta, x, and y. If we keep the alpha, the beta, the x, and the y in play, you know, the same 4 things, looking at it x tensor y acting on alpha, beta versus alpha tensor beta acting on x, y, yeah, we're going to get the same result. That's true. They are equal. So do you guys understand? I mean, I can go through the calculation again, but the calculation is the one we just went through, right? What I do to prove this, right? If I just plug in alpha and beta here, would it help you guys to see that calculation? I mean, I can do it. So like g of alpha comma beta is g of the sum over I of alpha lower I, e upper I, sum over j, beta lower j, e upper j. Since g is bilinear, I can pull out the summations. I can pull out the constants. And that leaves me with g of ei, e upper j, which we're going to define to be g upper ij. And I probably need another lemma, don't I? Maybe I need a lemma number 2. See, alpha lower I is really, I guess this, we already proved this today. I just need to look back earlier in the lecture. What was the ith component of the dual vector in this world of calculation? It was what? It's alpha of what? Alpha of ei, and that's beta of ej. To calculate the ith component of alpha, we operate alpha on the basis, the ith basis vector, and likewise for beta j. And then that is, by the definition of the tensor product again, gij e lower I tensor e lower j acting on alpha beta, and then I just go ahead and pull the sum out. Which shows you, since that holds for all alpha beta, that the theorem over there is legit. Since this is true for all inputs, it then follows that my formula over there is a reasonable one. I'm showing I can build the function g from a sum of the tensor products, of the vectors here. Are we good? Yeah.
Would it be academic nonsense to say your second to last term is gij alpha cross beta, or alpha tensor beta, beta of j?
You want to write this as, instead, you're like, no, I refuse your formula and I trade your formula for a different formula, namely that this is alpha tensor beta